So these are vocabulary terms you would need to know in order to understand gravity. Mass affects gravitational force. Mass is an object's resistance to acceleration. Gravity, self-explanatory there. Radius, when we're talking about gravity, radius can be somewhat considered the distance between the two objects that you're talking about. Now, a lot of time, those are planets orbiting other massive objects, or moons orbiting planets, or something like that. So a lot of times we're talking about circles, and when we say radius, we just mean the distance between the two center of gravities of those two orbiting objects. So radius is basically distance when we're talking about gravity. And finally, constant, a number that does not change. There's the gravitational constant, which we'll talk about soon. Let's move on to this. So gravity, the concept has been around for a long time, but it wasn't until like Isaac Newton, 1679. You've probably heard of the apple tree fell on him. Well, may or may not be true, but the force that holds the moon to the Earth and the apple falling down to the Earth, they're the same force. They're gravitational force. So all objects with mass in this universe are attracted to each other if they have mass by a gravitational force. So you on the Earth, you're pulled to the Earth, but the Earth is also pulled towards you. The apple pulled to the Earth is also pulled towards the apple. Same thing for the moon. That's why the moon doesn't fly away. It's held to the Earth by Earth's gravitational force. Objects with mass have gravity. Now, here's the thing. Even light, which you wouldn't normally think of as having mass, can be affected by gravity. So if you concentrate enough light in one spot, you could actually make a black hole out of it. Or the light leaving a black hole or a white dwarf or a neutron star is actually redshifted as gravity pulls back on the light and stretches out the wavelength. So things you wouldn't normally think of can actually be affected by gravity as well, and time. But that is definitely not anything to do with Newton's law of gravity. So moving on from that, you may have heard of the concept of weight before. So weight, mass times gravity, will be 9.8 meters per second squared. That's the gravitational acceleration of Earth. Well, weight is just your mass times 9.8 meters per second squared. So here is the formula for universal gravitation to find the force of gravity. There is 4 parts to it. There is big G, which we'll talk about soon. There is M, which stands for mass. Now you see in this formula there is M1 and M2. So the mass of object 1 and the mass of object 2. That 1 and the 2 aren't actual real numbers. So you can actually leave those out of writing the formula if you want. I would recommend it. It doesn't matter which one goes first, because with multiplication, you can switch up the order and it's the same number. Now on the bottom there, you can see that it has R, and that R stands for radius. And it's not just R, it's radius squared. So the more distance you have between two objects, the less force of gravity you'll have. We'll see more on that later. The more mass you have, the more gravity you'll have. And now you can change it around a little bit. Like I said, you can take away the 1 and the 2. We can put the number in for G. So for example, instead of putting G, you can actually put in 6.67 times 10 to the negative 11th into your formula if you want to do that. By all means, whatever works best for you. Now for G, we know that M is mass, R is distance, G is the constant of proportionality. And what it does is it just stays that number the whole time. It's always going to be 6.67 times 10 to the negative 11th. The units are Newton meter squared over kilogram squared. Now, most questions, you're just going to see unitless because when it all works out, the units will just be newtons. But definitely write down the number, 6.67 times 10 to the negative 11th. If you want to put that in your formula for G, that's fine. If you want to write G and then move the formula later, that's fine as well. That number will always be that number. It is not going to change anytime soon. And if it does change, that's going to change some things about our universe. So for example, if that number got bigger, you might see more black holes. If that number got smaller, stars might not fuse anymore. So it's good that that number stays the same. Some tips when calculating gravity. So if you're looking at big objects like planets or stars, they will have a big gravitational force. You might even see it written as scientific notation. If you have a small object, so if you're looking at the gravitational force between 2 guinea pigs or between your computer and you might see a very small number for the gravitational force, something like maybe 3.27 times 10 to the negative 16th power. And it makes sense. Small objects don't exert that much gravity. It's not like you're being pulled toward your computer screen right now. It's very, very, very small gravitational force, not as much as the Earth. So right now, you're only really feeling the Earth, not, a tiny computer near you or your desk or the floor or something like that. Units for mass, kilograms, and the units for distance, meters. They'll always be presented to that, so you don't need to convert. That's good. And when calculating the formula, I always recommend do the exponents, PERMDAS, then multiply the top, and then divide by the bottom. Now, here's our first example. So for the inverse square law, when two objects get farther away, their gravitational force drops. As two objects get closer, their gravitational force increases. Now, it's not a linear increase. Like if you double the distance, it doesn't double the amount of gravity that drops. No. It's exponential increase. So if two objects get twice as far away, their gravitational force drops by 4 times as much. If they get 2 times closer, then the gravitational force increases by 4 times as much. Increase it by 3 times. So let's say they get 3 times farther away, their gravitational force drops 9 times as much. So that's why something like the sun, which has a lot of mass, we don't really feel the sun's gravity when it passes overhead. It's just so far away that its gravitational force is arguably tiny compared to even the Earth or the moon even. So the moon will actually have a bigger effect than the sun because the moon is a lot closer, even though it's a lot less massive. Now, this also brings up another thing, black holes. Black holes do not suck, okay? Black holes have gravity, just like stars have gravity and planets and everything else. If you were to take our sun and turn it into a black hole, which you wouldn't be able to, but let's assume you magically were able to do that, all the planets would continue to orbit the black hole. All the moons, everything would orbit like nothing had changed. The only difference is everything would be frozen because there was no starlight. It would not suck any of the planets in or anything like that. So black holes have the same mass that they did before they became black holes, which means they have the same gravity as they did before they became black holes. The only difference is you can get a lot closer to a black hole than you could a star. If you try getting this close to the star, you'd burn up. You can get much closer to one of these, which means you would be able to feel more gravitational force. So black holes are no different than any other massive object. Now, there's a graphing example, a graph of what we'd see as you got closer or farther away from an object. So let's say you start at one distance, whatever that is. If you got twice as far away from an object, the gravitational force would drop off to 1/4 as much. If you got to 3 times as far away from an object, you would feel 1/9 the gravitational force. 4 times as much, so you get 4 times farther away, you would feel 1/16 the gravitational force. So you can see as you get farther away, gravitational force drops down. As you get closer to an object, gravitational force increases. Look, it practically spikes up to vertical as you get closer and closer to an object. So at half the distance, you would feel 4 times the force. At a fourth of the distance, you feel 16 times more force. So closer, more gravity, farther away, less gravity. Here's our